to okay, EI L equals to 1L equals to 1 EI. Alright, and then let's say, let's put it this way, like first of all, your matrix for the element you have the 4 by 4, but the big one for this thing here you have 6 by 6. Okay, so let me do it this way first. Let's see, 6 by 6. Okay, I put the big frame out there, and then you will be relevant to this one inside here. I put 0 first, hit Control Enter, you get all 0 there. Okay. So this column associated with U1, U2, U3, U4, U5, U6. Okay. U1, U6, right? Then, if you want, I insert this up. If you want to maybe conduct this, how to say, try to pull off the E, I, and L out of your matrix at this point, you get U2 multiplied by L, U4 multiplied by L, and U6 multiplied by L. Okay, so those rows will be, for example, a row of 6 over L squared, 4 over L minus 6 over L squared, minus 4 over L will turn out to be you get 6 over L squared, 4 over L squared, right? Minus 6 over L squared and 4 L squared. Okay. And then you multiply the whole line with the L for the line associated with U1, U2, U3. Okay, same as what I did here. Okay, to clear off the variables. So the variables, we pull them off like EI over L. This one I pull off the L square, right? EI over L square. Okay, over out there. And on the other side, you will have the WL square, WL square, WL square, WL square. Okay. So here will be equals to 12 times the scale of EI, alright, over the scale of L cube. Wait a second, nothing's wrong. I need to just put in the scale there. Oh, you have 2 EI in here. Okay. Alright. Likewise, equals to 6 times EI over L square. That one L cube. Okay, looks good. Equals to minus, equals to this one, equals to this one, equals to 4 times EI over L, equals to minus of this one, and equals to 0.5 of this one. Okay, and then easy, minus of this one equals to this one, the diagonal equals to this one, and equals to this one, and equals to this one, equals to this, and equals to this, and the last one equals to this one. If we change to 1, okay, 12, 6 minus 12, 6, 6, 4, 6, 2, minus 12, minus 6, 12, 6, minus 6, 6, 4, minus 6, 4. Okay, was good? Alright, what else that you have? Okay, I delete this one for time being. So this is multiply, okay, to this one here, and then add up to this one here. That is going to multiply by WL minus multiply by L, okay, WL square, alright? And that is going to be equal to, on this side, bang, bang. Okay, so here is your element. Okay. You don't have external force applied. Okay, you have the F1, F2, F3, okay, support reactions. Okay, over here on this side you have what? WL over 2, okay, which is 0.5, WL square over 12, but well, the line of WL over 2 I multiply through by the L, right? So you end up with WL square, like that one. The line number 5, the line U5, you get the L multiplied through. So instead of WL that you had before, then it turns out to be WL square. So everything can be inside this vector, okay, and then scale by WL square. So 1 over 12 is 0.0833. Oh well, I just make it this way. 1 over 12. I just need here is equals to this one, and here is equals to minus of this one, and then you have 0, 0. Okay, not relevant. Okay, this is known. Okay, known from the first element. Okay, right, done for the first element. Second element, copy, paste. Number 2, just make it 1, okay, and clear this off first. Oh, I just want to make it this way. Will it be allowed? Sorry, then do you want to make it? Yes. Why not? Okay. And then 0, 0. Alright. So make it like this. Pick this one up. And here. And black it off. What do we have here? We have 0.25, and then something which is equals to half of this one. Basically, I just can copy it down because it is half of that one. Okay. All right. I get this. And for here, I zero it off first. do we have? We have the point force, okay, acting over like 0.4 acting here, right? Minus 0.4 and minus 0.05. Okay. So here, but this one is F3, okay. All right. What next? Stopping down. I say, I don't care anything about anything inside there. I say the whole assembly. Okay, the system of equation. Okay. So we are talking about all the elements, alright? I said that this is a superposition of this with this one, okay? Because I add them into the same big matrix, and then I copy down, and then I copy that way, right? Okay. I think this looks like the thing behind the board, but you will need to add the spring stiffness to the degree of freedom number 4. So you add it by how much? 10. Get 22 there. And degree of freedom number 5, that you have the vertical spring of 60. Okay, 72. Essentially, if you look at these 3, okay. Yeah. Now, okay, let's fix this one first. This one is the combination of this add up with this, and then copy down. Done. Now on this side, F1 still F1, okay, F2, F3. These 3 are unknowns, and we know these 3. Okay. All right. So let's equals to here, and then down. How could structural analysis be this casual? It looks so easy. Just put things in there. Okay. So you conduct the row and column elimination in here. Now your matrix is going to be this guy, right? 1 second, which is equals to this side minus this side, right? Copy down. I don't want the format. Okay, just like the format. Multiply by here. So you want to calculate this, which is equals to MMULT, matrix multiplication of M inverse this matrix, and then you multiply to this matrix to close the bracket, before you hit enter, you hold the control and the shift and then enter. You get this one. And here. And the scale over here is W L to the 4th divided by EI. That's it. Right? So, let's see. Equals to 1 divided by 1, 460. Right? Equals to what? Minus 551 over 52560 equals to minus 53 over 2920. Okay, looks good. Now, structural analysis. You don't need SAP for the frame. Come on, or for the beam. You just Excel, and it's like you are chatting with friends in the Sunday afternoon. It is quite relaxing. A cup of coffee, drink, and then analysis is done quite easily. Now support reactions. So if I need support, I will send you this file. Okay, so you can crack it out. Find join in this support reactions. You need support reactions. You need to copy this part of the matrix, as this will be multiplied to 0. So you copy this one. Okay. And then multiply by what? By this one, which is equals to okay. You multiply by this one. What is the scale? I bring out the scale. So out here you have EIL squared. In here you have what? WL squared over EI. So EI cancel out. Elsewhere you end up with WL squared, right? So WL squared, and then okay, these two multiply, add up with what? This come from this point, right? And then copy it down. How's the roller coaster? You freak out already? You lose conscious? Okay, equals to F1, F2, F3. F1, F2, F3 will be just a number. Okay, so this is the scale of the number. So if you want, you can clear this out, right? WL squared, WL squared, WL squared. So you get just the coefficients. So F1, F2, F3 will be equals to what? This this is equals to this one, add up with MULT, matrix multiplication of this one and this one. Close it, shift, control, enter, got it. Done. It is not that done because you have two spring forces to determine, right? So spring force to determine, let's say K superscript R and K superscript translation, okay, which is actually I do the subscript 4 and I do the subscript 5. Okay, they are equals to, what is the number 4? Spring stiffness is equals to 10. Alright, 10 EI over L multiplied by the U4, which is here, no, equals to this multiplied by 10. Okay, right? But okay, anyway, that's the force that is occur in spring if you take the spring stiffness multiplied by the rotation. Okay, that's the force that is occur in spring. Now you want to know the force that is occurred into your structure. Easy. You have spring. For example, you push it down, so your displacement will be minus delta. Okay. Your displacement minus delta, you have the K. So your force is equal to K times the minus delta. This is the force that your spring feels, right? It feels this force. If I am the spring, I feel that someone is trying to push me down. Okay. Vice versa. If I am the structure is here. So structure is on there, and then spring force is pushing the structure up. Okay, so it is the negative of K times displacement U. So put the negative sign, okay, times the U times the spring stiffness, you end up with this. Likewise, for the other tip, so you have the 60 multiplied, minus 60 multiplied by this. So here is it. This is multiplied by W, what is that now? WL 4 over EI, and then you multiply by EI over L cubed, so this turns out to be WL, and this is multiplied WL times L, WL squared, right? Done, done, done. What else you want to know? Further from this point, I don't teach, so you go find BMD by yourself. You go find shear force diagram by yourself. That will be all. Okay. Now, how could we enrich this problem? Enrich sounds like scary. Oh, by the way, we don't enrich anything to this problem now. Well, you want to put the curvature from temperature effects, that will be just you just have more ingredients to put into this soup, alright? But this soup is cooked in the same way, okay? Nothing tricky is different. This is based upon the row and column elimination. ELIM. Okay. Row column elimination. We just did the first one. Next, what? I copy this. Next is I talk about 3, right? Right. The second technique is so-called penalty method. Penalty method. How does it work? Penalty methods gonna use the, well, you think of the column, the fixed cantilever support column, okay? Not column, sorry, the beam, okay, cantilever beam like this. At the support, if you look at the support like a spring, okay, look at the support like a spring. So your spring that is extremely stiff. So you put large spring stiffness in there in your stiffness matrix. So as the spring gets stiffer and stiffer and stiffer, your displacement will be smaller and smaller and smaller. So if it is huge, then displacement will be approaching to 0. But you cannot put infinity in your matrix, right? If you put infinity in your matrix, what's gonna happen? You look at the matrix like this, and then maybe you put infinity here, okay? When we look into this matrix, you're gonna feel like this is like, when you scale this, normalize this matrix, you divide by infinity. So you have 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay? You will be approaching to that condition. The matrix will be so-called like ill condition. The ill condition matrix, what is the problem? So if it looks like 1 and 0, 0, 0, 0, 0, that means your inversion will not be possible because your determinant will be 0. Okay, your determinant is 0, so when you conduct, you perform the inversion of the matrix, you're going to have 1 over determinant in the term there. Alright? And then 1 over 0 is undefined. So when you have too large penalty spring coefficients plugged in, you will end up with some problem. It depends on what program you use. MATLAB, you might be so large somewhere. Okay, Excel, you can go up to maybe this large, different large. Okay, but when it is way too large, you end up with problem. So, what could be the best values to put in? You look onto these diagonal lines. Maybe you pick up the biggest one. Alright? You pick up the biggest one and then you multiply the biggest one by 1 million. 10 to the 6, 10 to the 5, 10 to the 6, 10 to the 7. Okay? So make it big, but just that big, not necessary to make like 10 to the power of 100. Okay? Might be too big. Alright, but keep in mind, the bigger the better, because you will get the 0 that is closer to 0. You will get close to perfect 0. Otherwise, when it is not big enough, then at the point that you were supposed to get 0, you might get 0.0004. Okay, if you want to get 0.0000001, then you got to get like 10 to the power of quite large. But again, numerical stability is the issue. However, if you do this penalty spring, what is good for you? It is the way for the lazy guy, okay, to work. So sometimes if I'm lazy, I just use this technique. Because you have nothing to do with, you don't need to, how to say, you don't need to modify your matrix. You have the 6 by 6 matrix. This is the only technique that you don't need to modify. So if you use row and column elimination, you got to eliminate row, eliminate columns. That is friendly for you when you are in the exam. When you do homework, when you do hand calculation, very friendly. When it is in computer programming, you got to come and eliminate rows, eliminate columns. You got to write the code, and then when the row shifts, then the index of the row changes, and then you have to okay, take care of those matters. But for penalty techniques, all right. So we have the K, we have the U, and we have the fixed-end reactions equals to externally applied force, okay? You will only have externally applied force. You will not have reaction force. Why? Because reaction force has transformed into spring force. So you think of this case. You have spring. Spring is already taken care in your system of equation, right? You add the spring in there, okay, it works. So instead of making it like a support, you just make it spring. I make vertical spring and rotational spring, okay, and vertical spring over here. So now spring takes care of that F, okay? So that F you had before, gone. You don't have support reactions because support reaction turns into the form of spring force. You get my point? You add the K. You add the K, alright? This is K spring. So once you add the K spring, support reaction that used to be the unknown has been eliminated because you have spring force in here. So 0, 0, 0, 0, and then some value and some value, just like that. This is the beauty of this technique. So you don't need, once you have 0 here on the right hand side, would that bother you? It's not going to bother you because you still have only just known values on the right hand side. Okay, life is beautiful. Now, U1, U2, U3, U4, U5, U6, you may not say that it is beautiful here because previously U1, U2, U3 are known to be 0, right? This time they are close to 0, but they are non-zero. Okay, you get this point? This is the way it works. So no longer that U1, U2, U3 are 0. So you cannot remove the row and column associated with U1, U2, U3. They are non-zero, but they are extremely small. Okay, all right. So you put these 3 guys back into the system of equations, and you say that they are non-zero. You need to solve for them. Of course, you will solve for them and you get something close to 0, and you cannot drop off because some value that is close to 0 will be multiplied by the big value of K, and then you will end up with support reactions. This support reaction does not show up over here because it is there already. Okay? Here's the mechanism. Now, okay, anybody is just off the roller coaster on the way? I can repeat for another time from which point if you want. Okay? You want? Yes, another round for the penalty method, right? Okay. So penalty method. You don't do anything. Okay, first you start from element matrix. You assemble element matrix into the whole system, okay, of your structure. Okay, that's your assembly. So put together, okay, many elements. Okay, you have this equation. But let's revisit. Previously, you just say that. Previously you just say that this is equal to 0. This and this. You 1, 2, 3 equals to 0. So you take the 0, multiply by the first 3 columns, and then you say that why do we need to keep the first 3 columns if they are multiplied to 0? So we just eliminate column. After you eliminate this column, as you know the u, okay, and as they are support, and the support you have support reaction. Right? If it is a support, you have support reaction. So support reaction pops up here. F1, F2, F3. Okay. And as they are unknown, you don't like them, so you clean off these 3 first rows. That is the technique for row and column elimination. Handy, because you will just need to work on this part, smaller equation, but it's very efficient. But you need to adjust your matrix. If you use penalty method, you don't disturb the system much, because now you allow this gang to be non-zero, even though they are very small, close to 0, but still they are non-zero. So we say that, okay, why not? If the support moves 0.1 microns, what's gonna be the problem, right? So we make you throw in the big number, okay? Maybe 10 to the 6 times the K max on your diagonal. So you find on the diagonal line which one is the biggest here. Okay, you pick one, multiply times 10 to the 6. Okay, then you stuff it in. Okay, so now you make the support being the spring, but very stiff spring. That means support will slightly move, just a little bit, but still satisfy our requirement. Okay, let the support move a little bit. Why not? It's too small, negligible. Okay, so you add big values in there. So it is just like the way you treat those springs. Okay, it is nothing new. You add it to the diagonal that is associated with your degree of freedom that you introduce. Okay, add in here, then you allow 1, 2, 3 to be non-zero. Okay, these 3 are non-zero but small. Now you remove the support, you replace by the spring. That means the force at your support is coming from this big value of the spring stiffness multiplied by this very small value of the displacement. These 2 multiply, you get support reactions. So you cannot have support reaction here. You remove the fixed support, you put spring instead. You don't have support anymore. So these 3 goes to hell, right? Boom, boom, boom. 0, because you have nothing applied at these 3 points. This is how beautiful it is, because 0, 0, 0 and the other points, you know the quantities. Okay, at the other point that it is not the support, you know force quantity that is applied. So that will be the natural boundary conditions that you know force. So everything in here on the right hand side is known. Don't touch it. It is good. You have fixed end reaction. Just leave it like that. You push it to the other side. You can fix. Your analysis is done. This side you keep these three. Okay. Then your matrix will not be disturbed. All right. The remaining three will always be unknown still. All right. And then that's it. So let's try by penalty method. Okay. Over here. It will be quick. So I don't do this anymore. Element number 1, element number 2, assemble into system of equations. Okay, we are at this point before we apply the scheme of row column or penalty. So over here, I will then clean this off. Alright. Okay. So our system of equation just looks like this. But for the penalty method, you have nothing. Okay, you cannot have these force reactions. 0 means 0, okay? There is no apply point forces, moments, at the nodes. Okay, and then you end up with these figures here. Black it off, do it this way. Okay, now penalty spring. Here I highlight it, here I highlight, and the last one. These three are the candidates. Okay, because they are support. But as we remove the support by having the right hand side force unknown on the right hand side cleared off, so you add the spring in here. Penalty spring, you want to make it like 10 to the 6 times of the, you add it, okay, add a huge spring in there, 10 to the 6 times of the figures on the diagonal. The maximum one on the diagonal is 72, so let's make it add up with 72, 1, 2, 3, 4, 5, 6. Okay. Yeah, you just simply add this spring in there, and then add it, and then add it in. Okay. That will be it. So on this side, it's supposed to be this side minus this one, right? You move this to the other side, okay, times the WL is equals to this okay, wait a minute, I just okay. Right, so the next line will be just equals to MMULT matrix multiplication of M inverse of this matrix times this one. Okay. What do you see? Highlight these three up. Go back to this page. Where is 0068, 0105, 0182, 0068, 01048, okay, 0182, pretty much the same. And I just copy the value and then paste it there side by side. Why? I need value. Not bad. Just a little bit difference. So one is from the row in column eliminations and another one from penalty methods. Work for both. Now let's have fun. So I make it K penalty. Let's put it K penalty. Okay, so let's call this one penalty spring stiffness equals to 1e to 1000, which equals to 1e. Okay, right. So this figure is 10 to the power of 100. Okay, I make it 1000. Do you want to accept? No. Okay. Is it too big that program cannot handle more than 100? Okay, so that's the best that the program can do. 10 to the 100. So you have 100 zeros in there. Okay, instead of this value, I just make it this one. I just make it this one. Okay, still work? Okay, not fun. 9. Still work? Not fun. Still work. And how could I gotta win. I just know that. It doesn't accept 500. One E 500. Okay, fine, I can do it. Equals to 1 equals to 10, 100 to the power of, yes. Okay. Now it's in trouble. It doesn't recognize this number. That is not a good. Okay, it doesn't recognize what? Okay. Number error. It's not like the matrix is not good enough to produce the inverse. Okay, it is number error. I don't like that. I want the the problem in matrix inversion, but now it doesn't recognize this number. Now it recognizes, but when it recognizes, it still comes up with figures, with solutions. Okay, fine. All right, let Excel good can handle this crazy calculation. Okay, U4, U5, U6 are identical to the previous solution. Now you want to find the support reactions. Okay, so support reactions. So I call it F1, F2, F3. Okay, F4, F5. So what is this? Oh, by the way, please look at these three. They are extremely small. The value is like infinitesimal. Okay, the dust, star dust compared to the galaxy. Okay, like that. But even though they are extremely small like this, they are still useful for you because you're going to take minus of the displacement multiplied by that. Okay. 0.5, 0.8. Yes. Alright. And well, I should, the J27 is a stiffness. I lock it like this. Okay. And then copy down. Bang bang. Okay. 8.61, 7 point, yeah. Right? 7 point something. Okay. So let's say everything that I mentioned, just like what I mentioned on Tuesday. If something goes wrong, if you cannot match between two schemes, blame nobody, not yourself. Okay? If I do it wrong, I'm gonna blame myself also. Sometimes I show up in here, I can go wrong, and then I will just find out what's wrong with my calculation. But there's nobody to blame, but just yourself. Number 4, what is the stiffness for minus 10? Okay, times that 4. So this is not so interesting anymore because it's just minus 60, 50, 60, 60 times this one, 1.8. Okay. $11. Okay, good enough. Next time we will continue with the Lagrange multiplier. So we're gonna use these spreadsheets and then play with Lagrange multiplier for you next time. Hey, but by the way, today, right? The most important thing for today.